Lee is an associate professor in the graduate program chair in the Department of Grain Science and Industry at K-State. Dr. Lee's research focuses on understanding the structure, chemistry, and functionality of grain proteins and bioactive peptides with the aim of developing high-quality, functional, grain-based foods, ingredients, and nutraceuticals. He and his team employ and integrate wet chemistry, engineering principles, computational simulation, and applied machine learning to deepen the knowledge and advance the research on proteins and peptides. Since joining the faculty in 2016, Dr. Lee has received over $4.3 million in research funding as a lead PI from sources such as the USDA, Kansas Grain Commissions, and the grain and food industries. Dr. Lee has published more than 130 journal articles, and he's associate editor for both Journal of Food Science and Cereal Chemistry, and serves on the editorial boards of multiple international journals. Dr. Guo is an assistant professor in the Department of Electrical and Computer Engineering at Kansas State University. He earned his PhD in Electrical and Computer Engineering from the University of Florida in 2019. His research focuses on large language models, formal verification, and hardware security. He has received several accolades, including Best Paper Awards at DATE 2019 and Asian Host 2020, and a Best Paper nomination at ASP DAC 2021. He was honored with the Outstanding Assistant Professor Award from the Carl R. Ice College of Engineering at K-State, as well as the first award and REI Award from Kansas NSF F-Score. Most recently, he is the recipient of the 2024 NSF Career Award.
Okay, thank you for the nice introduction. So let's start our talk today. I will work with Dr. Lee presenting our project, our collaborations, specifically securing the future of antimicrobial research, AI-driven data integrity, and cybersecurity for bioinformatics. So, okay. No response? No response? Okay, it's okay. Let's use the. Okay. Okay. So here is today's outline. First of all, I will introduce our recent NSF project supporting our work now, safeguarding AI in bioinformatics, enhancing cybersecurity in biologic data infrastructure. And from the name, you may have already have the feeling that okay, it includes two parts actually. First is in the cybersecurity. The other part is in the bioinformatics. So the next, I will give a brief introduction about the cyber attacks for the current generative AI. And also, Dr. Lee will give a talk regarding the bioinformatics. And then in the last 5 minutes, there will be a Q&A. So that's today's schedule. And now let's start with our NSF project, safeguarding AI in bioinformatics. And then, since the topic is AI, of course, now everyone knows that AI is a very hot topic. And recently, the big news for the AI, of course, the Nobel Prize, right? So 2 Nobel Prizes in the physics and chemistries are given to the researchers in the AI area, especially for the second one, for the chemistry Nobel Prize is given to the researchers who developed the AI for predicting the protein structure. And our work we will share today also work on predicting the protein and the peptide structure, but focus on the cybersecurity side. So what's that? Of course, this time, let me introduce a little bit about the NSF project supporting our work. So it's NSF Cybersecurity Innovation for Cyber Infrastructure CSI program, usable and collaborative security for science area. And this project is a 3-year project starting from this year, and the PIs Dr. Lee and I from the Kansas State University and Dr. Yang from the Michigan Technological University working on this project. And then before coming here, I asked the ChatGPT that, okay, please draw me a picture that what come to people's mind when they hear the following words together: AI, bio, and cybersecurity. Then ChatGPT have me draw, give me a lot of pictures, very cute, but a little bit scary pictures. I select 2 of them. So that leads to a question: what are we are doing now? What's our research? What we want to do? So this is what we want to do. We hope to solve the security problem from the integration of AI and bioinformatics. So since bioinformatics is a very large area, so we particularly focus on the antimicrobial peptides and proteins. So in short, we call it AMPS. And why the AI and the anti-peptide and proteins, the collaboration will introduce the cybersecurity risks, because how the AI works in those areas. So nowadays, people, Dr. please correct me if I made a mistake, because I'm a cybersecurity researcher and I know some domain knowledge from Dr. Lee's team. So nowadays, people using the generative AI to help predict the structure of the peptide and proteins. So here, in fact, include a question here. So no one care about the data side that is utilized to train that AI. So is the data side used to train that domain-specific AI being checked or being security verified? So from my viewpoint, from a cybersecurity researcher viewpoint, no, not at all. For instance, the Unicorn, the largest data set in the bioinformatics. Although there are some review mechanism included for those data sets, but those mechanism just like check if the data comes from a paper, if the author or organization exists or not. But no one really check what information or data contained included in that data set. From the security perspective, no one do the security check. And where the problem will be happened? So since AI, nowadays AI really got a lot of achievements. However, it also extend the attack surface from the attacker side, which means that we have more space. The attacker has more space to carry out, to perform attack. For instance, the backdoor attack, the data poisoning are all targeted to all for the AI. And those attacks had already been happened in many other domains. For instance, the computer vision, the natural language processing, and other domains. So there's another question: what's the difference of the peptide and proteins? So if the attack happened in a computer system like the computer vision, so the worst case is that we can change another computer, right? But how about some malicious logic embedded in the protein? Those may become the medicine or the food. Then some terrible result may be happened. So one result will be like the manipulated data can lead to the high cost regarding timing and money in the wet lab. Because after getting the prediction of structure from the AI, we need to validate if the structure works or not. So we need to do the wet lab, and the wet lab is very expensive. If then the manipulated data may lead to the result that, okay, this prediction looks good, but after the wet lab, it shows that, okay, in fact, it does not work at all. Or some even worse situations that the backdoor or Trojan from the maybe also can be exhibited in the protein structure, which means that without the trigger, the protein looks the same. But once there's some condition added, then the protein or the peptide become some other materials. So those kind of cyber attacks, since it had already been happened in other area, can it be possible to happen in the bioinformatics? So our work, we are working on answering this question. If it happened, what would be the solution? So here is our proposed solution. So first of all, we will develop a model graph model for analyzing the anti-peptide and protein structures. Then the next job is we will try to filtering those low quality data from data set to make sure that there is a more accuracy in predicting the high quality structure. And then we will focus on investigating if the data poisoning or backdoor attack can be existed in the anti-peptide and protein area. And if there are some attacks for that, what should we develop the defenses? And then in the end, so from the security researcher perspective, for all the security mechanism, we better avoid the people's or the manually work. So we will develop the automatic tools to help filtering the data, detecting the vulnerabilities, and protecting the whole data set. So that is our solution. If successful, then so it will help in identify and mitigate the vulnerability in the AMP data, of course. And then we hope to build a zero trust framework in the scientific collaborations, which means that a scientist should not worry about if they do not familiar with that collaborator, they can still trust the data from that collaborator. No malicious data will be hidden behind. And also, we will provide the robust cybersecurity checking tools for the AMP area. And of course, in the end, we will open source our tools and open source all our data sets for training the AI in the domain-specific area, in the AMP area. So that's what we want to do. So let's go to the next question, next part. So is what are the attacks for the generative AI nowadays? But before that, let me introduce a little bit of background regarding the generative AI, or we can treat it as a large language model like ChatGPT. So for the generative AI, especially large language model, in short, LLM, has been deeply integrated into the modern life. So according to a very recent survey given by the Microsoft and the LinkedIn, so across major cities, 75 of people had already been using the AI at their work. And 46 of them start using it in less than 6 months, which means that in half a year, the AI population doubled. And also, this is not only happening in the young generation. Employees across every group are bringing their own AI tools to work. So this is very useful data. And of course, in the domain-specific areas, the AI is used everywhere. So I'm from computer engineering, so I'm more familiar with the semiconductor industry. So if you check the large language model space and semiconductor or your own area, you can find a lot of events and papers on the industry side and on the academia side. And then before really introducing the attack, let me bring another background about how does the LLM, the large language model, or ChatGPT work. So the working principle of LLM is a mechanism for making the prediction for the next token. So based on this algorithm, a lot of attack will be happening. So then the input, like in the left side, so the input is first tokenized and embedded into the space. We assume that there is space for the LLM. Then using the self-attention mechanism for each token, the LLM calculates the weight between any token connected to each other. And then after passing a multiple multi-layer perception, in short MLP, it finally outputs a group of probabilities. Then what will be the next word generated by the AI, by the LLM, will be decided by those probabilities. Therefore, to lead the LLM to generate some malicious information, so the key point is how to adjust those probabilities. And so then another background knowledge that domain-specific generative AI, LLM. So since we need to use the LLM in the bioinformatics, therefore it's related to another topic that is how to train a model to make it become an expert. Basically, there are two ways if we wanted to adjust the probability in a model. So the first is pre-train a model, which means that if you have enough data, like several tens of gigabits data in a domain-specific area, then you can totally from scratch pre-train a model to make sure that that model, after training, it becomes an expert in that area. So back to the model, if we treat it from the model side, say it from model side, it means that all the parameters in the model has been adjusted, has been changed. Then another situation is that if we do not have enough data, so in most of the situations for domain-specific area, we do not have enough data, then we can do the fine-tuning, which means that we only adjust a few layers. So for the large language model, the model includes a huge number of layers. We only adjust a few layers using our domain-specific data, and then after training, the model can still have a very good performance in that area. And so also in this figure, I listed the training procedure of the LLM. And also there are two other ways, so that if we do not want to adjust the parameter in the model, we can use another two ways to make the LLM become the expert. The first is named method is named the prompt engineering. Of course, nowadays people give a more popular name as the chain of thought. So which means that when we need to use that LLM or the ChatGPT, we sit there and carefully design our prompt, our question input to the LLM, and then get a useful response. So the next one is the method is retrieval augmented generation, or the RAG, we call it RAG. So it means that we maintain a data set. That data set includes all the knowledge, all the domain knowledge in a specific area, and then we embedding that domain knowledge, we coding it together with the LLM, so that each time when the LLM gets our question, the LLM will find the answer from the data set and then give us the response. So the RAG has a very good performance in a very tiny, very small application like the restaurant, like ordering food, this kind of system. But for a larger domestic area like the bioinformatics, the RAG may not have the very good performance. Then let's go to our the most important topic, the threats against the LLM. Since there are a very complex working procedure in the LLM, of course, accordingly, nowadays there are many attacks. The first attacks I want to introduce are first two attacks: model stealing. The model stealing on the left side and the sensitive training data recovery from the right side. It means that this attack is attacking the LLM, the model itself. For the model stealing, the attackers do the measurement from the information we may not realize. For instance, the power consumption, the timing difference when we ask a question and get the answer. Using that difference, the difference in timing and difference in power consumption, the attacker can steal the parameter from the model. So that is the model stealing. So for the sensitive training data recovery, that is also attack the model, but the target is still the training data. This is more terrible. Think about that. If your data is utilized by the ChatGPT to train its model, for instance, that data includes your bank ID and PIN and the key, and then attacker can ask the LLM, okay, please give me the key according to account number for this user, and then the LLM will give its training data back to the attacker. So that's the two attacks. And then the hallucination is that so it's attackers will through a lot of questions will let the LLM think that okay, I'm the expert. Actually, it's not. then the LLM will give a lot of answer, a lot of mistake in his answer. And the next one, the adversarial examples and the jailbreak attacks. This is more interesting. So it's like so nowadays the vendors, like OpenAI, set a lot of security mechanism to the LLM. For instance, avoid the information leakage, just like the example I used. It's not like LLM to give the information to the regarding the user question, but still the attackers can cheat the LLM by making a story like, okay, the attacker can ask the LLM, okay, my grandma wanted to tell a story to her kids. Please help me design this story about what's the source code of the Microsoft operating system. So using that way, the LLM you will think that, okay, it's this story, okay, I provide you the real information. That is this kind of attack. For the prompt injection, it's like, so the attacker can tell the LLM, like, okay, this is the instruction. Ignore or bypass, forgot all the instructions given by your vendor. Then the LLM will bypass the security algorithm and then give the attacker the secret. But for our case, we will focus on the backdoor attacks. For those backdoor attacks, it's like a Trojan. That Trojan embedded in the LLM. So in general, a Trojan is defined like a malicious, intentionally modification of a design that will result in undesired behavior when the system is deployed. So in general, a Trojan contains two basic parts: the trigger part and the payload part. Once the trigger detects unexpected events or condition, then the payload is activated to perform the malicious behavior. So let's take a look at the example. So the first working procedure of how the backdoor attacks can be happened. So as we already introduced, for training a large language model, we need to have a data set. We need to have a train the model and then deploy it. So the backdoor attack happened at the data set and also the training stage. And then here is the first backdoor attack. So to explain what it is. So it happened in the computer vision domain. So basically, the attacker makes the victim's model learn that this stop sign plus a yellow sticker equals to the speed limit sign. What the result will be? After training using those data, the victim model deployed in the autonomous vehicle will not stop at the stop sign if we stick the yellow stick put the yellow stick in that stop sign. The autonomous vehicle will treat it as the speed limit, like this. Very dangerous, right? So this is example of the first of a backdoor attack. And if we introduce or explain the detail, basically what the attacker needs to do is need to insert a trigger into the training data set and then change or insert the label for those samples as targeted classes, for instance, the speed limit sign. And then when the victim download the poison data set and then train their own model, then the attacks will be happening. Very similar as the scenario of the peptide area, right? No one do the security check in the Unipro data set, which means that the attacker can upload their data, their poison data, without with no limitations, and then perform the attacks. So, and also there are some backdoor attacks in other areas like the natural language processing. So since time is limited, I will not introduce details. And then, so we need to answer a question like, will this kind of attack really be happened in the bioinformatics area? So for that question, we need more domain knowledge. Than we are working on that in answering this question. So let's go to the next part from the Dr. Lee regarding for the bioinformatics. And in the meanwhile, yeah, thanks ANSF again. And also I put the QR code here for regarding my lab. If you are interested, scan the QR code. You can find several selected data set and model from my team, and feel free to reach out. Okay, let's totally take over work.
Okay, so good morning. Now it's my turn. So I'm Yonghui Li from Green Science. With Dr. Guo's background on the cybersecurity. So now we kind of switch the gear a little bit to the bioinformatics, its application in the bioactive peptides and also from food protein. So here's my outline. I'm going to start with some background on the bioactive peptides that you are not familiar, and also we'll move to our work on the wet chemistry for the discovery of bioactive peptides. And then we move to prediction with those more like regular machine learning, and then move to the large language model, accelerated predictions. So about active peptides, they are protein fragments. So you're about 2 to 20 amino acid residues, and then some they would have those called health beneficial biological effects. One example is antimicrobial peptides, and as we will focus on our NSF project. But also we work, antioxidant, antimicrobial, anti-cancer, anti-diabetic. There are different types of the biofunctions, the peptide they could possess. And then for the production of the peptide, the typical ways to start with protein. We have the natural protein and we hydrolyze. We use enzyme to break down the protein into fragments. And then we do a lot of those like separations, purification to concentrate those functional peptides. So that's the most common process. But also, people working on the synthesize start with amino acids, and then they do those like traditional, solid states synthesis to produce a peptide from amino acid. That'd be more costly. And then, really, it's a very growing market for the application as nutraceuticals, pharmaceuticals, or as some like food additive for the ingredients. One example for the the application of the peptides is a value addition to the agricultural byproduct. We use this fish meal as example. If you search for the price, it's about like $2 per kilogram. But then if we turn those fish meal into the protein hydrolysis with some bioactivity, now the price, it actually is sold by like per capsule. If you turn to a kilogram, it's going to be like 300 per kilogram. We just add a lot of value by turning those like waste into some high value peptides. And then if you did like further, purifications, concentration of the peptide into those ACE, so that's with some like anti-hypertensive functions. Now you are getting even like higher value with those hydrolysis or the peptides. So there are actually some commercial bioactive peptides or protein hydrolysis from, like the whey protein, from rice protein, from, casein. There are different examples. It is commercially available, but we want to, add more value with those, like from grain, from cereal, from other low-cost proteins into those bioactive peptides. The typical wet lab procedure to produce peptides is we start with the raw material like sorghum protein or like sorghum meal or corn meal or wheat protein, and then we do the extraction of the protein to get higher like protein concentration, and then we do the hydrolysis with an enzyme. So that's probably the most important part, like really which enzyme or which combination of enzyme to use, because different enzyme would break down the protein at different positions. And that would lead to a composition of the peptide with very different, sequences, structures, composition, and functions. That's a key step. After that, we do a series of those fractionation and purification process, try to concentrate those functional peptides. And then we run like the mass spectroscopy to, to identify the sequences of the functional peptides. Okay. And then for the application, we evaluate this project, we focus on the antioxidant. So we evaluate that performance, in this different, like those systems, like emotions, fat, pet food, or even bakery. So this shows example, after we have the hydrolysis from corn gluten meal, we did the separation with the ultrafiltration, mammary filtration. That's a pretty common, commercial process to do some separation. And then we have like different size of those peptides and a very crude separation. And we can see they actually have different antioxidant properties. And then after that, we also did this chromatography. This is based on the site exclusion chromatography. So we can actually further have more like those detailed or more like this target separation of the peptide by their size. And then we again, look into those concentrated fraction with a higher antioxidant activity. And then we run like the reverse phase HPLC with the mass spectroscopy, look into like those fragments and also their compilations. And then for the application, so we look at them as antioxidant. So this is water, is water in oil. Actually, it's oil in water in motion. And then we add like different concentration of these peptides. See, can they really slow down the oxidation of the fat? And very promising compared to the control. With addition of those peptides, now the oxidation gets much slower. So that shows very promising antioxidant properties of those corn peptides. And the same thing for this ground meat. So we add this peptides into the ground pork. So compared to the control, you got very fast oxidation. And then with addition of this like different concentration of the peptides, we slow down the fat oxidation in the, in those ground meat. And then mostly a lot of antioxidants, they could also have some anti-cancer properties. So we did start look into the anti-cancer. We use the HepG2, that's a liver cancer cell model. And then even we have control, that means there's no antioxidant. And then with different concentration of these core peptides. So as we can see from our data, actually with addition of these core peptides, it's going to slow down the growth of those cancer cells. So that again shows some like potential of those peptides as anti-cancer compounds. Okay, so based on those like previous work, we can see like this chemistry process is very tedious, very kind of long process with all the separation, purification, concentration, the sequence identification, very long process, very costly. And then we are asking, can we have some way to make the process faster or more efficient? Because you naturally run like millions of peptides, you could get suppose like 20 natural amino acids, and then you got like different size of the peptides that just create like really just a lot of the combinations. So that's why we came to this bioinformatics tools. So bioinformatics is interdisciplinary between the biological science, statistics, and computer science. It kind of combines those different disciplines, and then with like there's some tools we can use for the bioactive peptides. So we actually we have a paper recently. We kind of really give a critical review on the previous work on the application of the bioinformatics tools into the bioactive peptides. We highlight those like the QSAR as a quantitative structure application relationship modeling, or machine learning, deep learning, docking, or the MD simulation. There's like different tools. That has been a very hot area, and also we are working in a similar area. So for this talk, I'm going to focus on the application of the machine learning, for those peptide research. So for the machine learning of the data, that's for the first important part, how we get the high quality data sets. And also, with very, there's no toxic data there, as Dr. Guo, explained. And next step is the feature extraction with the peptides, especially with label the peptide. How can we really extract those most critical features that can, have some impact on those final properties? So feature extraction is another important process. And then after that, the selection of the algorithm, right, different machine learning or deep learning or the transformer algorithm, which work best for the specific situation. And then we need to do like the validation of the model and then use the model. Okay, so as mentioned earlier, so really how we can better represent the peptide, that's a key question, really how we're going to extract the most useful features from the peptides. There are typically different ways. So when we use global descriptors based on those amino acid compositions, physical chemical properties, all those information of the sequences, or we have like those sequence-based representation. So that's mostly applied to like large language models with those pre-trained protein large language model. They can actually provide a lot of contextual, very useful information on the peptide, to embed those peptide information. Or we can, consider the peptide sequence as a graph, and then we can extract those nodes and aid information from the peptides to have the embeddings. Or we can use like additional 3D structure, like from AlphaFold or from other, like the model, we can predict, or we can actually get the structures of the real 3D structure of the peptide and then do a further representation of their information. or we can do a combination of the multi-features for the representation of the peptides. Okay, so we had work earlier in the prediction of this tripeptides antioxidant. So we got the data about 130 labeled data, not very big, but it was okay for our application. And then we compare like different feature extraction method and also different machine learning models. And then at the end, we actually predict some, very promising peptides, tripeptides, and then we synthesize, and then, we did those external experimental validation of their antioxidant properties. So as you can see, from the different combination of the feature selection with the different machine learning models, we got like a lot of those, like the scenario models. We found like the best model actually is we use the random forest as a feature selection. And then we use the tree-based XGBoost for the, as a modeling, as an algorithm. We achieve the R square from the cross validation about 0.87. So that's actually pretty promising and exceeded all the previous, models. And also with that QSAR model, we were able to really conclude like the feature important or relative like the importance of the features. What we found actually, as a tripeptide are 3 residues, the inside one, the central one, and the C-side one. The model actually tells us actually those C terminal residues more important for determining this antioxidant properties. And then at the end, we can predict those like 8,000 tripeptides, those majority, were not reported before. So we can actually give those like the prediction values on their relative antioxidant strengths. And also, from the predictions, we can conclude there are 30 residues that are really important for the antioxidant tripeptide, like tyrosine or tryptophan or cysteine, the C terminal is very important. And then we select 6 tripeptides with very high, medium, and low antioxidant values. We synthesize the peptides, and then we get the data. We measure the data from the lab, and we compare with the predictions. Actually, overall, it's a very good, relatively good consistency between the predictions and our experimental testing. Okay, so for the feature selection, that's very critical, how we can extract the most important features. That's why we use machine learning, but now we're back to those language models with those actually pre-trained large language model called protein large language model. They can actually going to have provide a lot of useful information, for the further fine-tuning or the transfer learning. So one example, we use the ESM. So that's actually a model from Meta AI. They started in 2019, and they finally published last year in Science. So that's a very good model. So they got ESM2 as their the pre-trained lab model, and they apply for the protein structure prediction. So what they found actually their ESM2 fold is actually even better or even faster compared to the AlphaFold 2. AlphaFold, that's a Nobel Prize model, but now ESM2 is even more powerful, at least faster compared to the AlphaFold. So then we use this ESM2, to do the embedding of our peptides compared to the traditional method. There's other like like global descriptors, like the AAC, amino acid compositions, the DPC, different way to do the embedding. We compare with the ESM2 with large language model. And then after that embedding, we use different classifiers to do the prediction. So from embedding, you can see actually compare the ESM2 with those traditional global descriptors. Actually, ESM2 is really good. You can see like ESM2 can very well, with the ESM2 embedding, it can very well separate those positive data from negative data. You can see a very good separation. But for majority of the traditional embeddings, they are hard to really use. They cannot separate those different labels. And then from the model performance, that definitely very, confirm our hypothesis. So basically, all the ESM2 based embeddings and then outperform other traditional embeddings. Of course, like the classifier, the model also important, but at least combined with the ESM2 give a much better performance. And then we ask ourselves, can we even make it more powerful? Can we really, with the ESM2, can we do like a really universal model for the prediction of the peptide and the proteins? Excuse me. Yeah, so then we can get different data sets, different bioactivities, actually 20 different biofunctions of the peptides. And then we use ESM2 as our embedding method. And then we connect with the neural network for the classification prediction. Okay, so those are the data sets we use or different function. You like the ACE, that's the anti-hypertensive property, the antimicrobial, anti-diabetics, or those like antioxidant different functions. We use different data sets and we kind of separately to do the transfer learning from our with our architecture. And that what we found actually this model really achieved very good performance. Like for the 15 of the 20 functions, it outperformed the previous models. And then for the other 5, it's actually very comparable to the previous models. So what that shows really, we have one model, it can solve everything, but then previously you got 20 models to do 20 work. You got antioxidant in one model, you got antimicrobial in another model. But for us, we got one model, it's like one stop for all those peptide related function prediction. Okay, so besides the ESM2, there are actually other models, other large language models. So there's ESM2, there's ProBird, there's like those they protest different protein language model. So we were thinking, do they perform similarly? Can we find some like even better protein language model for our peptides, compared to the ESM2? So then we did another work. This focused on the antimicrobial peptides, particularly those like cell penetrating peptides. They are a very big group of the antimicrobials. We got the data set and then we use like the different protein language model as the embedding method for our peptides. And then we connect with the neural network as a classifier and look into their functions. So the paper is currently under review, but the general conclusion is actually ESM2 is still very good compared to those previous protein language model. So far, the ESM2 from Meta AI is still the most powerful, the language model for our peptide application. So in addition to those machine learning and deep learning, we have also used this molecular modeling for the peptides and antimicrobial peptide research. So one work we did is we use the molecular dynamic simulation to look into like the interactions between the peptides and the microbials. If you think from previous prediction, the model tells us there might be like 100 peptides, they have potential antimicrobial properties. But then we have to do additional validation of the 100, that's still a lot of work to do. So then we were thinking, can we combine with additional screening tool like the MD simulation to look into there and to further refine those most promising peptides. Okay, and also with the MD simulation, can also look into the interaction with how the peptides interact with the microbial cell memories. So that's also going to provide additional real mechanism information for us. Again, this paper is also under review currently. So hopefully within the next few months we can get that paper published. So back to the protein, I'm from Green Science. So can we ask how we can apply those models or the simulation of prediction to our protein, corn protein or sorghum protein? So then we have another model or called in silico work. We can actually do those simulated hydrolysis without doing a real experiment to break down the peptide, to break down protein. Now we actually put the protein sequences into our platform, and then we can select different enzyme, one enzyme or multi-enzyme at different orders, look into the potential peptide, make it 5,000 peptides from sorghum protein with hydrolysis of trypsin and pepsi, and then we can put the 5,000 peptides into our model for the screening. So basically, we can make everything in silico. At the end, now we got a promising peptide. Now we can do the work, to do the real productions. Okay, so those are the takeaways. Because time, I'm not going to read all the details, but basically show that the bioinformatics tools can be very helpful for our peptides and protein research. And we do have funding from USDA and also very soon from SF for the supporting of our peptide research. So that's all my talk. Thank you. Thank you, everyone. Any questions, please? Yeah, either to me or to Dr. Guo.
Any questions?
So we are here.
Regarding the computer side and the bio side.
Yes, please.
Yeah, sure.
What? Lipopeptides. Yeah, that's something we haven't really tapped into, but I think it's another interesting area, but we haven't worked on that.
So where do you envision your research going in the next few years? Like, where do you think this is going to go?
Yeah, I would say definitely like with the new SF grants. So those work like what I introduced here from our like last 5-6 years. But for now, we can combine those like different data sets for our protein peptides with Dr. Guo's work on the cybersecurity. That's going to definitely create a lot of new learnings, but also very useful to our like those bioinformatics area. And Dr. Guo
Yeah, it's a large language model area. So recording, right? Okay. Because recently the OpenAI was looking for money, so they tell a lot of stories. So one story was like, okay, after like 1,000 days, the real intelligence will come. We do not know if it's true or false. But overall, the generative AI, especially large language model, will be keep popular for at least for the next 1 or 2 years. This is my insight for this area, and also interdiscipline collaboration in different area like the computer, security, AI, bio will be a trend. Through a lot of conference I attended, so we can see that okay, find a lot of good points in this area, in the collaboration area will be a trend for the entire research. Yeah.
You mentioned that it might make it easier or better for sharing data between collaborators.
Yeah.
And there's more security.
Yeah, very good question. Yeah, this kind of question, in fact, have a problem, or we call it a privacy problem, or the security problem, happened in a lot of areas, especially in my own area, the semiconductor. So it's like, all the researchers or people, we need the data, but all the data are from the big companies. They refuse to share the data. Privacy issue, that's of course first. And second is that the security issue. If I share my data and then you use it to train a model, how can you make sure that my information will not be leaked? That's the second question. The third question is that there are malicious people, they are attackers. They will share some malicious data with the poisoning data included in it. How to deal with that problem? So that is our future research or work we are doing right now. So we hope to automatically check the security for all the data source from different branch, from different domain, to make sure that at least there is a very low probability to those data will be will have some harmful or malicious impact for people's work.
How can we improve that in K-State itself, even across campus? Because this is a discussion already at the moment on research.
So yeah, very good question. Yeah, how to prove it in the K-State? So I think if I did this work first, I will collect the data from different areas and then figure it out what's the real domain-specific security issue in that area. Because in each direction or research area, the privacy or security problem will be different. So and then I will use split the data into the testing data and the training data, and then verify if that data will lead to some malicious attack locally. And then after that, maybe some online or cloud-based solution will be deployed. So that, which means that when the attacker, when a user or researchers want to do the security check, upload their data to our cloud tools, and then do a security check. Yeah.
So if somebody, what is your advice for PIs and researchers that currently work with machine learning, sensitive data? What are some things that you would advise them to do to secure that data, knowing what you know about how those systems work? So if they integrate AI into their research, is there something they should do to protect their data?
Yeah, maybe Dr. Guo can
Yeah,
answer.
yeah. Since it's related to sensitive data now, it's I know there are some tools to it's like okay, so encrypt the data first, but even with the interaction encryption or coding your data first, encoding your data first, and then your data can still be utilized in the machine learning. That's one way. But I do not think many researchers, especially not the researchers not from computer area, they will accept those tools. So unfortunately, right now, those kind of collaboration based on the trust, which means that you trust your collaborator. Yeah, that's the only solution right now. But in future, we expect some tools, security tools, to come out for real use. But in the meanwhile, with a very low learning curve.
Is there someone or a group at K-State that can vet machine learning software to make sure it is secure before people use it with their research?
I think so. Maybe yeah, we need to reach out to the researchers in the computer science. Yeah, they are working on it.
That'd be nice to have somewhere that people can say, I want to do research. Here's AI or machine learning that I want to integrate. Can you tell me if this is safe? So,
Yes, exactly. And the key point for doing that is that we need to let more and more computer science researchers know have the domain specific knowledge. It's very, very hard to know another knowledge from other domain. Yeah.
That's why we collaborate. Right?
Yes.
Before, Dr. Guo came to me to discuss that proposal, we never think about like really cybersecurity could be a concern for our bioinformatics. Basically we share everything. When we publish, we share all the code, all the data, we make everything online to everyone. But then actually he reminded us there could be cybersecurity concern. That's why we came to this like a proposal and then lead to that SF project.
No questions? No questions from the Zoom? I do not think so.
there's none.
No.
Thank you.
Okay, thank you.
Thank you. Thank you, everyone.